Global population is growing fast, with an estimated increase of 2 billion people in the next 30 years. And as more people move to cities, demand for minerals is soaring. Minerals are everywhere: the buildings we live in, the cars we drive, the mobile phones we use. And as we shift to renewable low-carbon energy, there's even greater pressure on metal supply.
If we want to make the future energy transition come true, then as a society we have to consider alternative options to source the raw materials we need.
The answer may lie at the bottom of the ocean, in the Clarion-Clipperton Zone in the Pacific. Here, 5 kilometers beneath the ocean surface, lie billions of potato-sized rocks called polymetallic nodules. They contain the metals we need for a clean energy future: nickel, cobalt, copper, and manganese. But reaching these nodules isn't easy. And over the past 40 years, scientists and engineers have been exploring the possibility of collecting them. The EU has funded a number of projects related to deep-sea mining. The latest is Blue Nodules, partnering leading academic and industry figures to further develop the technology to mine nodules from the seafloor with minimum environmental impact, including loss to biodiversity. The focus has been on developing a mining vehicle and the flow process, while considering the impact of sediment plumes, compaction of the seabed, and noise.
This is a new industry, and we have a unique opportunity to address these environmental issues from the outset. We can find out how far we can push the technology and the operations to achieve the goal of deep-sea mining while causing the least environmental damage.
Once the surface operation vessel is located over the mine site, the seafloor nodule collector is lowered to the seabed. The collector is connected by an umbilical cable that transmits power and communication signals. It's also connected via a vertical transport system, or riser pipe, that will transfer the ore from the seabed to the surface operation vessel. The seabed is composed of soft muds with nodules lying strewn across the surface, which are removed from the mud as part of the mining process. The collector uses water jets to blast the nodules free, but also creates clouds of unwanted sediment that are sucked up too. Each hour of operation will recover around 400 tons of nodules from a mined area of approximately 0.03 square kilometers. Similar to other extractive industries, small animals living in the sediment and attached to the nodules will be removed. In an area such as the Clarion-Clipperton Zone, recolonization may take a very long time. As the collector mines, noise will be generated, and the weight of the vehicle may compact the seabed. Inside the vehicle, the sediment needs to be separated as much as possible from the nodules. To achieve this, a simple inclined tube with an upward water flow has been designed, in which the nodules slide downwards and the sediment is ejected at the top of the tube, passing to the rear of the collector where it's released as a slurry. This mostly deposits on the seabed behind the collector, but some remain suspended in the water, forming a sediment plume that's carried away from the mine site in the prevailing currents. When it settles, it may impact the seabed fauna, possibly outside the mined area. The nodules plus some sediment not removed are flushed into the jumper hose. This forms a flexible link between the collector and the metal riser pipe, allowing the collector to mine backwards and forwards on predetermined mining tracks. From here, the nodules are pumped up the riser pipe on their 5-kilometer journey to the surface operation vessel. Pumps are located every kilometer and will generate noise. The larger nodules will be broken as they pass through the pumps. So the material arriving at the ship will consist of water derived near the seabed, sediment not removed at the seabed, plus nodules and a limited amount of nodule fragments. This material must be dewatered, as nodules need to be stored in a dry state. Water is removed using equipment developed for the offshore dredging industry, such as sieve screens and hydrocyclones. But not all sediment can be removed. So when this water is returned to the ocean, it forms a sediment plume, which is carried by currents and may impact animals living at different depths depending on where the water is released. The nodules need to be stored on the surface operation vessel, where they wait to be offloaded onto bulk carriers. When the carriers arrive, perhaps once a week, the nodules are either re-wetted to be transferred in a wet state, which then requires further dewatering, or in a dry state by conveyor. IHC have designed the seafloor nodule collector, taking into account the environmental work carried out in the project. The first vehicle developed was the Apollo 1 to test functioning of the propulsion system. Its successor, the larger Apollo 2, was developed to test general functioning and the collection system. This vehicle has 4 tracks, increasing maneuverability, efficiency, and reducing the sediment plume. It was important to limit its weight, so it is made of lightweight materials. It's electrically powered to make it as energy efficient as possible. And after testing both a mechanical and jet collector, the jet collector option was chosen for its robust design. The full-scale vehicle will have all the basic features of the Apollo 2, including being all-electric with the 4-track layout. The jet collector will be a 16-meter wide modular design. Contitech have been developing the jumper hose, the flexible connection between the collector and the riser pipe. It's a challenging engineering task where validation and testing take high priority. Various tests were conducted on bending stiffness, axial pulling, and full-scale wear to validate operational parameters. Destructive tests were conducted to determine the limits of construction. Direct have been developing the umbilical system that connects the ship to the mining vehicle, delivering power, communications, and lifting ability. It is able to work at 5.5 kilometers water depth for a period of over 20 years. Developing a rapid and safe deployment and recovery of the transport system was key. The answer lies in a simple yet inventive method to clamp the umbilical to the riser pipe, saving time and reducing risk. The scaled test vehicle Apollo 2 was tested in the Bay of Malaga off Spain during 2 field trials, following extensive lab testing of the propulsion and collector systems by IHC engineers.
Field tests had 2 goals. The first goal was to test the functionality and the performance of the vehicle. The second test was to determine the environmental impact of the operation. During the first field test, we had some issues with our monitoring and control system, caused by some faulty readings from one of our sensors. We had to use manual steering for the heading system. It was very helpful to have some time between the 2 field tests. It could improve the efficiency and reliability of the vehicle, and everything went smoothly during the second field test. Currently, we're continuing the development of the vehicle and the collecting system. The major goal of the development is to further reduce the impact on the environment.
IHC MTI, Aachen University, and Dredging International each contributed to research and testing related to the flow process from the seabed to the shore. IHC-MTI focused on how this process could impact the nodules and if they become reduced in size.
Our main objective in the Blue Nodules project was answering the question what the quality of the produced polymetallic nodules would be. During transport, the polymetallic nodules will degrade. And there's a lower limit in particle size below which you have to consider the material as waste.
This helps calculate the volume of the ore that can be used, the volume of waste returned to the sea and its potential impact, and informs the design criteria for separation and processing. The nodules are first separated from the sediment on seafloor level. Aachen University designed and built a rotating cleaning drum to achieve this.
We carried out several tests with a declined drum and a horizontal drum in order to see if the declined drum has any positive effect on the efficiency. The losses during the tests were only 5% of nodules, whereas the efficiency was about 80%, and even our best results with the declined drum were over 90%.
From the seafloor, the nodules are transported more than 5 kilometers to the surface vessel. Tests were carried out to simulate how they could be impacted on this journey.
We designed purpose-built experiments to investigate the different degradation processes. We studied impact fragmentation, which occurs when a nodule hits a surface. We studied chipping and attrition, which happens when nodules interact during their way up. And we studied the abrasion of polymetallic nodules, which will happen when nodules slide over a surface. Adding up these three separate effects then gives you the total degradation of these polymetallic nodules. We found out that the repeated impact fragmentation hardly contributes to finds in the waste stream. Abrasion, attrition and chipping on the other end, they do. With our mathematical framework on one hand and the dedicated experiments on the other, we are now able to actually predict the change in particle size distribution from seafloor to sea surface. And with these tools at hand, we can take a next step in optimization of these deep sea mining processes.
Once the slurry has been transported from the riser pipe to the surface vessel, the nodules are separated from the unwanted seawater and sediment by the dewatering system. Dredging International looked at different concepts for dewatering using screens to retain the coarser particles, with finer material dewatered in a centrifuge or a series of hydrocyclones.
The main reason why you want to dewater the nodules when transporting them to a transport ship is because of safety. Ships that are designed to carry dry loads, they cannot handle wet or moist loads. If you bring in a too wet payload in a ship that is designed for a dry cargo, it can lose its stability because the load under influences of waves and ship vibrations can start acting as a fluid instead of a stable dry load.
Once the nodules have been dewatered, the unwanted deep sea water and sediment must be returned to the sea. The characteristics of deep sea water differ from surface seawater. To avoid these waters mixing and to reduce the spread of the plume, the project recommends a return outlet close to the seabed.
In our final design, we aim to combine two pipes clamped together. So one riser pipe which brings up the nodules, and then a second pipe with similar dimensions which brings the water pumped up back to the seafloor where it originally was sourced from. So by doing so, we invest in more complex, more expensive technology, but we reduce our environmental impacts and make it more controllable and more localized.
Once the nodules have been processed, they must be transferred from the support vessel to the transport vessel that will convey them to shore. Dredging International evaluated two different methods: a pump and floating pipeline system and a conveyor belt system.
Both the dry and wet option have their advantages and their different disadvantages. The wet option is common technology. It's used in the dredging industry already, where we use a lot of floating pipelines to bring sand, for example, to artificial islands. But once arriving on the receiving vessel, you need to dewater the nodules before they can enter the cargo hold, and you also need to bring this transportation water back to the vessel, where you need to treat it further before releasing it into the environment. But on the other hand, the nodules themselves, they can be transported dryly without any transportation fluid, so they can just be discharged on the bulk carrier without any further post-processing, so that eases things on the side of the bulk carrier.
The project has looked for ways of minimizing the environmental impact of mining nodules from the seabed through improved equipment design. NEOS tested how the weight of the nodule collector could alter the seabed.
We conducted some tests of the impact of the tracks on the seabed, and these field trials, which we carried out offshore Spain, they provided a nice opportunity to see these tracks in action in a marine environment on soft seabed under conditions which are somehow comparable to what you might find in the deep sea. This compaction of the seabed may create a problem because it will increase the mechanical strength of the sediment. In other words, it will make it stiffer, and thereby it will become more difficult for animals living on the seabed to dig into the sediment in search of food or for shelter.
A remotely operated vehicle attached with video cameras collected underwater video and sonar images. Box core samples of the disturbed seabed were also obtained.
The sediment was compressed a few centimeters and pore space reduced a bit, but at the same time what we think is that this compaction may be not a major problem, because while this harvesting vehicle is collecting nodules, it will spit out sediment at the back of the vehicle, and that sediment will settle back and cover the seabed which has been affected by mining already. And this cover may be centimeters or possibly tens of centimeters thick of very watery, unstable sediment, which will make it hard for fauna to recolonize the mined seabed.
Noise generated by the nodule collector, pumps, and surface operations could also impact sea life. Research was conducted by the University of Catalonia.
There are many fish and there are crustaceans and there are many animals that can either hear or that can perceive sound and that are affected by sound in some way or another. And effects can be that they are injured, an effect can be that they cannot sense sounds either from themselves or from other animals in the environment, that the sound is masked. And it can induce behavioral changes, that they leave an area or go away.
Noise from the collector was monitored during the field trials, but results were limited by using a scaled-down model in shallow waters. This data was combined with published literature to do some initial modeling.
For us, the outcome of the Blue Nodules project is that the crawler is probably not the largest contributor to the background noise, and that we should avoid placing a pump at 1 kilometer depth where you have the sound channel. That would maximize the effect of the installation. Other than that, of course, we have to try to minimize the sound of the surface vessel, following also the IMO regulations, and do everything we can to minimize the sound in the vertical transport system.
The sediment plumes generated by the mining process and the release of the returned water from dewatering on the support vessel may also create an impact to the ecosystem.
In the mining area itself and in the immediate surroundings of the mining area, there may be so much sediment settling out from these plumes that it's enough to bury and kill animals living on the seabed. And then further away, where these plumes are dispersed by currents, the high concentrations of suspended particles in the seawater may cause problems to animals by clogging feeding and breathing apparatuses. Certain animals, they like sponges, they may be able to shake off the drape of settled sediment, but others simply can't. But even if they can shake off this sediment, this will go at the cost of energy, and energy is very scarce in this deep sea environment.
Aarhus University developed a computer model called Flexum, which gives a prediction based on particle size, the settling velocity of the particles, and the local current carrying the plume away from the mine site. During the field trials, data on plumes was collected, which can be used to aid the model for the spread of plumes and predict their possible impact.
After doing these 2 field tests offshore Spain, there's still a lot to do. And what we hope to do in a follow-up project, we will continue with these tests and then try to produce a fully developed plume and also try different settings of the diffuser, the outlet which is producing this plume. And then what we ultimately hope to achieve is that we have good scientific data, good observations about how these plumes behave, and properly validated computer models predicting the spreading of these plumes. And with those, that we have a good basis to predict the impact of mining and of the plumes produced by mining in the deep sea environment. If in future deep sea mining will be growing into a full-blown industry, we hope that our results from Blue Nodules will contribute to keep its impact on the deep sea environment as low as possible, reduce the impact that mining will have on deep sea life.
So this is the end of the Blue Nodules project, but it's not the end of the deep sea mining journey. Still a lot needs to be done to make deep sea mining an industry that brings the minerals to establish a greener future for all. But I'm sure that with the network and friendship that we've established in this project, we can make this work. Thank you.